to your next lesson. I am Mrs. Thompson, and today we will be talking about parametric equations. Objectives are understanding parametric equations, graphing and understanding graphs of parametric equations, eliminating the parameter, in other words, eliminating the parametric portion from the equation, returning it to rectangular form, writing parametric equations, and exploring an application of parametric equations. Parametric equations are usually used to determine the motion of an object over time. That object could be a moving object or traveling object, such as an airplane, or it could be an object in your body or in someone's body, unfortunately, such as cancer cells moving, in other words, growing or hopefully decreasing in size due to treatment. Looking at an example, graphing parametric equations. We are also asked to identify the domain and the range. The parametric equations given are x equals 4 minus 3t and y equals 3 minus t. So parametric equations are given in pairs. In other words, they are given by telling us how the x values are changing as time goes on, and likewise how the y values are changing as time goes on. And for this particular example, we are told that the values of t are greater than or equal to 1 and less than or equal to 3. So, to graph, we simply plug in values for t and solve for x, and likewise plug in values for t and solve for 1. That has been done here in the table for this example. Discussing one of these, I'll go with the one in the middle. So plugging in 3 for t and finding the x value, of course, that would be 3 times 3, which is 9, and 4 minus 9 is negative 5. Likewise, plugging in 3 for t and finding the y value. 3 minus 3 is 0, and therefore the y value is 0. The values that are plugged in for t are your choice, but they must fall within any given restrictions. And of course, the restrictions given this time, the values of 1, 2, and 3 fall within that restriction for t. So going ahead and plotting our points on the x and y axis. Of course, we have the point negative 5, 0 as the starting point, and the point 1, 2 as the finishing point. The point negative 2 and 1 is also on this graph, though it has not been enlarged. So the domain, the x values, they start at negative 5 and end at 1. Likewise, the range, how low and how high the graph is traveling, starts at 0 on the y-axis and goes to 2. These points are on the graphs, our endpoints. We have closed circles, and that is illustrated here in interval notation by using brackets. Looking at another example of graphing parametric equations. This time, the equations given to us are x equals 13 times the cosine of t and y equals 13 times the sine of t. As always, you plug in values for t of your choice. There are no restrictions this time. And you would solve for x and y. Though there are no restrictions on what you plug in for t, notice that whatever you plug in for t, you must take the cosine of that angle and also the sine of that angle. So the cosine and sine of that value must be calculated. Yes, you may use a calculator, but it is wise to choose values for t that you know the sine and cosine of. So choose angles that you know the sine and cosine of. And it's even wiser to choose angles that have sines and cosines that are numbers that are very easy to work with. So notice that I chose to plug in for t 0, pi by 2, pi, and 3 pi by 2 because all of these angles are on the x or y axis, making the sines and cosines 0, 1, or -1, which are easy numbers to work with. Using pi by 2, which is of course the same as 90 degrees, as an example to discuss. If we plug in pi by 2 in the equation for x, the cosine of pi by 2 is 0, and 0 times 13 is 0, so the x value is 0. For y, if we plug in pi by 2 for sine, the sine of pi by 2 for our angle, the sine of pi by 2 is 1, and 1 times 13 is 13. Of course, the same procedure was used to find all the points. After finding the x and y values for your points, you will plot them. So, after finding the points, you must plot and connect them to make your graph. Notice that I used 4 points to make the graph. That was my personal choice. But 4 points was enough because thinking back to chapter 5, we know that the cosine function and the sine function, as we learn the sines and cosines around the unit circle, that the graph would be a circle, and these 4 points just confirm that for us. If you forgot that fact, then of course, with any graph, you should continue to plug in numbers and obtain points until you get enough points that you know how to connect them. In other words, if you're not sure whether to connect these 4 points using a square or a rectangle, continue to find points until you have enough that you know exactly how to connect them. You know how the graph is traveling. Moving right along, the next thing we will look at with our parametric equations is eliminating the parameter. So sometimes when an equation is given to us in parametric form, we're not able to identify how the graph will look, whether it will be a line, a parabola, or a circle, for example. So in that case, to assist with graphing, it is often wise to convert the equation from parametric form back to our rectangular system, which we are much more familiar with. Because as a reminder, in our rectangular coordinates system, we know that y equals mx plus b is a line, x minus h squared plus y minus k quantity squared equals the radius squared. That if our equation is in this form, the graph is a circle with center HK. And lastly, we know our quadratic equations, y equals ax squared plus bx plus c, that their graphs are parabolas. Looking at an example, eliminating the parameter. This experience will be similar to solving a system of equations. The parametric equations given to us are x equals 5t minus 1 and y equals 4t plus 6. Step 1. Solve the first equation for t. When we solve our first equation for t, the answer is t equals the sum x plus 1 divided by 5. Step 2. Plug in the results of step 1 into the second given equation. If we make that substitution, if we plug in for t what it is equal to into the second equation, we get y equals 4 times the quantity x plus 1 over 5 and then plus 6. Distributing and dividing the long fraction bar into its meaning, which is that both terms in the numerator share a denominator of 5. And lastly, combining the like terms of 4/5 plus 6, we get the equation y equals 4/5 x plus 34/5. If you decide to clear the fractions, you may by multiplying both sides by 5, and that would make the equation 5y minus 4x equals 34. So the parameter has been eliminated. We have the equation of a line in slope-intercept form, or in another very common form with x and y on the same side, but we know this is a line. We also know that it is a slanted line with a slope of 4/5. Any slanted line travels forever from the left to the right. So the domain is from negative infinity to positive infinity. It also forever travels from bottom to top along the y-axis. So likewise, the range is from negative infinity to positive infinity. If you decide to graph it, you can find 2 points on the graph, plot, and connect those points to graph the line. I select to find the x-intercept and y-intercept, but of course, any 2 points will do. We will cover the remainder of section 7.7 in another video. There we will look at writing parametric equations and a modeling application.